Welcome back. In the last session we had seen common base amplifier, and I told that we can use common base amplifier as a buffer amplifier for current. Therefore it is current buffer amplifier, and if you want to develop current amplifier, then we should use common base amplifier at the input and at the output, which is what is providing impedance matching for current amplification with respect to external source, current source, and external load where it takes the current. Okay. And this is what is the block diagram we discussed in the last session, right? And we added common base amplifier at the input as well as output. Now this is what your common emitter amplifier, which we are trying to extract current gain from common emitter amplifier. And if you see here, right, even though we are exciting with practical current source, because the input impedance of common base amplifier is very low, then almost its IS will enter into your common base amplifier, right? For example, if input impedance is not very high, then whatever IS you have, part of the current will enter into RS, part of the current will enter into your amplifier. Whatever current which is what is entering into your amplifier will amplify only that current. That is what we had seen in the case of common emitter amplifier, and then we got some current gain. But now to improve it, therefore, and to utilize whatever available gain or whatever maximum current gain we can get, we are inserting CB amplifier both at input as well as output. I am just explaining that part only. Therefore, now I already wrote here I1 is nothing but now IS, because RI is very low. Once the current which is entering into common base amplifier, then the current gain of common base amplifier is 1. Whatever current which is entering, same current will be coming out of common base amplifier and entering into common emitter amplifier. But remember, now for your common emitter amplifier, your common base amplifier is current source, because that is injecting the current. Okay. When I say this is what is current source, I want ideal current source with internal resistance infinity. Yes, it has infinity. I can say 1.3 mega ohm as infinity. Therefore, it is a current source, kind of ideal current source, or I can explain in a different way. This R0 is represented in shunt. Then now the input impedance of your common emitter amplifier is also like in shunt. Then there is a current source. Current always takes lowest resistance path, either entering into R0 or entering into Ri. R0 to Ri is very less. The entire current will enter into Ri, which is nothing but entering into your common emitter amplifier. That is nothing but what? That current is nothing but the current what you are getting from common base amplifier. That is IS. Therefore, IS is entering into common emitter amplifier. Whatever current which is entering into your amplifier, it will amplify the gain of AI. Therefore, which is nothing but AI into IS. AI into IS. That is what is after amplification. Now, for your common emitter amplifier, this is your actual load, but actual load is not connected. Common base amplifier is connected. Now, what is the input impedance of common base amplifier? 25 ohm, which is the load for your common emitter amplifier. Now, your common emitter amplifier is the source for your common base amplifier. When I say common emitter amplifier is the source for your common base amplifier, then whatever current you are getting, which is nothing but having R0 52K, now the input impedance is 25, the current whatever you are getting, which is AI into IS, R0 and then Ri, then instead of getting the current or entering into the R0, now entire current will be entering into Ri because of having low input impedance. That is what we need. We don't want to see the current which is bypassed by R0, which is shunt path, if it is a current source, which we don't want to see the current leakage or current reduction. I want to see AI into IS entirely entering into your common base amplifier. Yes, that is done because Ri is low. Once, therefore, the current which is what is coming out of your amplifier and then entering into common base amplifier is nothing but AI into IS. Right? Now, this current is entering into common base amplifier with gain of 1, then 1 into AI into IS. Therefore, this is what is giving current which is AI into IS, provided that is what is the maximum current it can give, and it has R0 1.3 mega ohm, RL, let us say the load is 10K. Therefore, we are always taking the example of load which is 10K. Okay? Then if this is what is the scenario, 1.3 mega ohm is very high, 10K is very low with respect to 1.3 mega ohm, then whatever current you are getting, which is AI into IS, it has two paths, either R0 or RL, because current always takes lowest resistance path. Current instead of entering into R0, it will enter into RL only. That is what we need. current should enter into your load, which is I into Is. Even though you have R0, but that is very high, because of which it is acting as a current source. I can say kind of ideal current source. Okay, that's why overall current gain we are getting from common emitter amplifier, and the impedance matching like source to load is through CB amplifier. But this is not familiar. Why this is not familiar? Because we don't want current amplifier. We want voltage amplifier. That part we had seen already. Okay, done. You take this. Now I'm giving you sufficient time to draw. Now take it. Then we will see the remaining theory. Now from this session onwards, this is not for workbook. We are not solving any workbook from now. It will take some time to start again workbook problems. Okay, we need to cover little theory. I think if the theory is over, then I can say the BJT small signal AC analysis. See, these are all these configurations will come under the topic BJT small signal AC analysis. Okay, but for one topic we need multiple sessions. Then for chapters we need to cover multiple topics. Different chapters, each chapter different topics, each topic multiple sessions. Okay, that is the methodology we are following. One more minute, then we can continue. Okay, I think till now whatever configurations we had seen, I can give you the summary. That summary is useful to compare between among all three configurations. Okay, after covering many topics, if you have summary, that is what is very important. That will help you to link from one concept to another concept. So always deal with observations, conclusions, summary. But you will get observations, conclusions, summary, right? First of all, to get observations, right, we need to have difference, need to cover all possible combinations or solutions. Then after observations, then from overall observations we can have conclusion. Then from multiple conclusions we can have summary. And summary is the one which is what is like summarizing the complete, I can say, a subject or topic. Okay. Write down summary. Don't write, I'll just give you a table, okay, with the values. Now this is common emitter configuration, common collector configuration, common base configuration. Okay. Now here this is what is AC parameter. Okay. Now the first one, right, that is nothing but if you want I can give you, that's fine. AI, therefore first one is AI, the current gain. For current gain, voltage gain, input impedance, output impedance. Okay. Now this is your current gain, voltage gain, input impedance, output impedance. The values what I am filling in the table, right, that is for RS is equal to 1 kilo ohm and RL is equal to 10 kilo ohm, and finally with BJT typical H parameters. Okay, with BJT typical H parameters which I gave, right? That is what, using those, right? Now if you see the current gain, what we got minus 40, voltage gain we got minus 400, input impedance we got 1 kilo ohm, output impedance we got 52 kilo ohm, right? We have very good current gain, very good voltage gain, but I already explained the meaning of minus. It is only direction. Okay, don't bother about the direction. If you take only magnitude 40 and then 400. Okay, therefore it has very good current gain, very good voltage gain inherently, but Ri 1K, R0 52K not having any impedance matching, means either Ri should be infinity or 0, or R0 should be infinity or 0. They should not comparable. They should not be comparable with source and load, right? If you see here Ri, what is your Rs? 1K comparable. Okay, R0 10K 52K almost comparable. Only 5 times is the difference. Okay, therefore there is no input impedance matching, or there is no impedance matching for both voltage amplification as well as current amplification, or etc. Now coming back to, therefore what is the observation here? The observation is very good voltage gain and current gain, but no impedance matching. No impedance matching. No impedance matching for what? For both voltage amplification as well as current amplification. You need to write for both voltage gain as well as current gain. That is what is your observation. Okay. but it has very good power gain. What is 40 into 400? 16,000 is the power gain. There is no configuration. You will see there is no configuration where you will get this much power gain. Okay, CE amplifier is the one which is what is giving you huge power gain, right? Now, if you take CC amplifier, what is current gain we got? We got 40. Voltage gain 1. Input impedance we got 400 kilo ohm, and output impedance we got 40 ohm. Therefore, tell me what is your observation. Now, if you look for Ri and R0, Ri 400K, if you compare with 1K, it is very high, right? Therefore, maybe I can write the comment, therefore, this is what is very high. Now, what about your R0? 40. If you compare with 10K, yes, this is low. But what is your voltage gain? This is unity. This is what is your observation, right? Therefore, what is your observation? Observation is very good impedance matching, very good impedance matching for voltage amplification, but your voltage gain is approximately equal to 1. It has very good impedance matching for voltage amplification, but voltage gain is equal to 1. Now, coming to common base amplifier, what is current gain? We got current gain 1, voltage gain we got 400, Ri we got 25 ohm, R0 we got 1.3 mega ohm. Now, if you observe clearly, right, with respect to Ri and R0, your 25 ohm with respect to 1K, I can say this is high, so sorry, this is low, and 1.3 mega ohm with respect to 10K, it is high. Therefore, it is providing very good impedance matching both at input and output for current amplification, but current gain is 1. Okay, therefore, very good impedance matching, very good impedance matching for current gain, but what is current gain? Current gain is approximately equal to 1, but current gain is approximately equal to 1, right? Therefore, this is what is unity. This is what we had seen already, the observations, but I am just keeping everything at the same time. That is what is our summary, right? We have few more observations, right? Before observing those things, you take this is summary. Remember, all these things we had seen already, but I am just putting in a table, okay? Therefore, it is easy to get the knowledge or easy to get the theory point. Take the table and then write below the table, write the observations below the table. I'll give you 1 more minute. The terms, the relative terms high and low, they are related to the source resistance and the load resistance. Okay, please make a note of it. That's why if you see the table something like this, we will get few more observations. That's what I was saying, right? After completing the table, we can see the remaining observations along with these observations. Now, tell me what is power gain of CC amplifier? Power gain is basically output power by input power. Okay? Therefore, that is nothing but voltage gain into current gain. Tell me what is power gain of CC amplifier? 40. And what is power gain of common base amplifier? 400. What is power gain of CE amplifier? 16,000, which is too significant, right? Because it has both voltage gain as well as current gain. Okay? And this is one of the observations. Therefore, by default, when I say if you don't bother about impedance part, and by default when I say an amplifier, therefore what is that amplifier? Blindly common emitter amplifier, because that is what is having huge power gain, right? To utilize huge power gain or to utilize either current gain or voltage gain, we can combine CC CB. That is what we did, right? To get impedance matching part, that is with respect to source and load, right? But anyway, the core of the amplifier, if you ask me, that is nothing but common emitter amplifier only. The core of the amplifier or the fundamental amplification, power amplification is happening through common emitter amplifier. Okay, that is one observation. And second observation I can say, if you observe clearly, one more point, what is maybe in the case of CC amplifier, it is having very good impedance matching for voltage amplification, but voltage gain is 1. Why are we not bothering about current gain? We have current gain also, right? Right? Even though we have current gain, that current gain, whatever impedance matching you have, right? That impedance matching is not favorable for the current gain. Okay, we will get current gain, right? But overall power gain, if you see, that is only 40. Therefore, we cannot utilize this 40 and we cannot improve this 40 further. But in the case of CE amplifier, even though I am saying 40, but if you put CB amplifier at the input, CB amplifier at the output, your current gain will be improved. By properly matching the impedances, the current gain can be improved. Okay. Now, the observation is, what is voltage gain of CC amplifier? 1. But what is current gain of CC amplifier? 40, which is exactly same as current gain of CE amplifier without inversion. CC amplifier current gain is nothing but CE amplifier current gain without inversion, approximately, neglecting 1 or 2% error. Now, taking common base amplifier, what is current gain of common base amplifier? 1, that is expected. But what is voltage gain of common base amplifier? 400, which is exactly same as in this table, exactly same as common emitter amplifier without inversion, right? Therefore, this is easy to remember, right? If you don't see this table, common emitter amplifier is providing very good voltage gain, very good current gain, but no proper impedance matching for any one of these two. Common collector amplifier is providing very good impedance matching for voltage amplification, but voltage gain is 1. Then what about current gain of common collector amplifier? Current gain of common collector amplifier is almost same as current gain of common emitter amplifier without inversion. Common base amplifier is providing very good impedance matching for current amplification, but current gain is equal to 1. Then the voltage gain of common base amplifier is almost same as the voltage gain of common emitter amplifier without inversion. Right? I hope this is clear, and this is what is very useful to summarize the configurations whatever we had seen till now. But except other than CE, CC, CB, we had seen two stages of CC, which is basically diode and pair, to improve the input impedance further. 400 kilo ohm became 1.8 mega ohm. That is what we had seen. Therefore, that is what is used at the first stage of your op amp. Okay. I hope this is done. Now let me explain the second, or I can say next topic, subtopic. I can say the topic is BJT small signal AC analysis. Under that, CE amplifier subtopic, CC amplifier subtopic, CB amplifier subtopic, diode and pair subtopic. Now another subtopic. That another subtopic is nothing but, you can say, simplified model. You can say simplified model. Simplified model. But I am going to give simplified model only for common emitter configuration. I am going to give for common emitter configuration. We can take for other two configurations, but based on the summary, right, what is the observation or what is the conclusion? When I say an amplifier, by default, that is nothing but common emitter amplifier. Therefore, you can say, when I say an amplifier, common emitter amplifier, because that is what is having huge power gain. The fundamental reason to choose a common emitter amplifier as the default amplifier is power gain. It has huge power gain. It can deliver more power to the load by taking DC power from your power supply. That is what your amplifier, right? I am repeating. Amplifier is a circuit which converts DC power into AC power under the guidance of input AC signal. But how much power it is taking from DC and then giving it to your load, then with respect to input power, therefore if you calculate the power gain, common emitter amplifier is the one which is what is providing huge power gain with respect to what? With respect to other two configurations. Therefore, common emitter amplifier can drive better loads. That is the meaning of it. That is the reason why default people pick up common emitter configuration and then continue. That's why maybe I can explain from this, saying that if you take all logic families, digital logic families, right? Even they are going to deal with the digits, logic 1, logic 0, logic 0, logic 1. In here also when you give logic 1, the gate or circuit should drive logic 0, means it has to drive the load, right? Therefore it has to have some driving capacity, right? The driving capacity is maximum in common emitter configuration. That's why if you take RTL, DTL, DL, emitter coupled logic, right? All these logic families are having common emitter configuration only. If you take resistor, transistor, this is nothing but RTL logic family, that is common emitter configuration. But we are going to keep the transistor in saturation and the cutoff on off to get digital action, but the configuration is common emitter configuration. That is very important point. That's why from now onwards when I speak about BJT, default common emitter configuration. When I speak about an amplifier, default common emitter amplifier. Okay, that is what done. Now when I say simplified model, when can you go for simplified model, right? Before saying what is simplified model, first of all, what do you have? Whatever H parameter model you have currently, right, which we got from two-port network analysis, remember that is what is called as exact model or a kind of practical model. This is like I can say whatever we had seen the diode approximations, right? Approximation 1, approximation 2, approximation 3, right? As the approximation level or as the level is increasing, we are going close to the exact equation. But here it is kind of opposite. Whatever we got two-port network model, people call it as somewhat practical or exact model. From that, if you reduce something, we'll come back to simplified model. I can say ideal model. That is nothing but your ideal model or level 1 model. Okay, that's fine. But if I say before going to simplified model, first of all, exact model. From exact model which is existing to simplified model. Okay. Now let's see what is exact model. Exact model is nothing but, therefore now we are covering what? We are covering concept. Okay. Not problems. We are covering concept. Therefore now the concept is here. You can keep in the box. This is easy to verify later to check. Now what is exact model? I am taking only CE configuration. Therefore if you take CE configuration, that is what is your transistor. Therefore this is what is your transistor. Again I am taking common emitter configuration structure or representation. This is collector, emitter, base. Okay. Now what is exact model we have seen? This is nothing but what? Having input. Therefore this is what your input and this is what your output. Okay. Therefore this is what your input VBE. This is what people say. This is VBE, small VBE, and this is what is small VCE, only AC signals, and the current which is entering into your base is nothing but small IB. The current which is entering into collector is nothing but small IC. Right? Input voltage, input current, output voltage, output current. Right? Two port network, input port, output port, but emitter is common for both the inputs. Right? Now if you take exact model, this is what is exact model. Right? Now this is nothing but VBE, the input voltage, and this is what is your IB. Earlier from two port network V1 I1, now specifically, right? Now this is for common emitter configuration, because default we got that default amplifier is, or default configuration is common emitter configuration, VBE and then IB, and we know this is nothing but having HIE, and we have this is nothing but HRE. I am using HRE into output voltage VCE, then this is HIE. Okay. Now this is what is your current source you have. This is HFE into input current IB, and we have 1 by HOE, 1 divided by HOE. Right? This is what is our, therefore this is base, this is emitter, similarly this is collector, this is emitter, and this is your VCE, and this is what is our collector current. Therefore this is what is our BJT exact model from two port network analysis, which we had seen already, but we didn't see directly like HRE, HFE, HOE represented in the equivalent circuit. We just had HI, HR, HF, HO, right? That was generic, but now it is specific to common emitter configuration. Okay. Now this is what we had seen, and then using this model only we solved all those formulae, we solved all those problems, and we derived AI, RI, R0, voltage gain. Okay. Now we can go to simplified model if you can neglect something. What can we neglect? If you neglect, then the model will become simple. That is what is called simplified model. Okay. If you neglect, then the model will become simple. Therefore that is nothing but your simplified model. Therefore if I go to simplified model, when can you go to simplified model? You can go to simplified model if you neglect. Therefore I am going from here to here. That is nothing but simplified model, deriving simplified model. Just listen here, don't write. I am giving the conditions. There are two conditions. Number one, to get simplified model. Number one, tell me what is HOE value 40K, right? Now let us say we are going to connect load here. When you connect load there, right? Now for example, whatever load you are connecting here, let us say that is 1K. If that is 1K and this is 40K, tell me this 40K is in parallel to your load, what you are going to connect here, which let us say that is 1K, 1K in parallel to 40K. Tell me 1K in parallel to 40K, approximately 1K. What does it mean? We can ignore the effect of 40K, means indirectly we can ignore ignore this branch, or you can take it as infinity, or you can neglect the parameter, right? Provided the load value is lesser. For what value of load we can neglect? That is what is the question now. Therefore, that is what people say, 10% of error can be introduced, which is the factor 0.1. Therefore, if the condition is, if HOE into RL is less than or equal to 0.1, if HOE into RL is less than or equal to 0.1, then neglect HOE. Neglect HOE means take HOE as 0. If you take HOE as 0, then what is 1 by 0 infinity means open the resistor. Then even though the resistor is present, which is 40K, along with 1K, then the 40K is not having any significance, you can neglect it, which is valid approximation, right? Even though we are getting simplified model, which is valid. But worst case, the error can be, because here the error can be 10%, that too only for current gain. Therefore now, tell me when can you, let us say if HOE is equal to 1 by 40K, then what is this value? To get the condition, what is this value? Then this is nothing but what? HOE 1 by 40K, right? Therefore I can say okay, 1 by 40K into RL should be less than or equal to 0.1, then RL should be less than or equal to 4 kilo ohm. If RL is less than or equal to 4 kilo ohm, neglect HOE. That is what it is saying. Means 40K, 4K, you can neglect approximately 40K, then you will get approximately 4K, right? But maximum error can be 10%. Okay, that is fine. Now, second one. We know that what is HRE value? HRE is equal to 2.5 into 10 to the power of minus 4, which is nothing but 0.00025. Take it as approximately 0 or take it as 0 if you go for simplified model, right? Simple, remember, mathematically or using H parameter model, there is no relation between HRE to HOE, right? But remember, qualitatively it has some link, it has some internal meaning related to base width modulation. If you neglect HOE, means if you take out that 1 by HOE branch, you have to consider HRE, which is very small, or you have to take HRE as 0, then you have to short it also. Whatever may be, for both, to go for simplified model, the condition is RL. If RL is in the order of 4K or less than 4K, right, then you can go for simply simplified model. Everybody understood? That is what it is. Then, for example, after neglecting these two, let's see what is the model, right? If you neglect those two, what do you get? Then the circuit will be, this is what is your HIE, then this is 0, then this is only current source, and this is what you have. That's it, right? This is your collector, emitter. Now this is nothing but HFE into IB, and this is what is your VBE, and this is what is your IB, and this is what is your IC, and this is what is your small VCE. Okay, this is what is your model, right? The same thing people calculate, or you can write the same thing as, maybe I don't have space here, let me write here the same thing. Maybe you can write like this. Both are same, only the connections what you show, that is what is different. This is collector, emitter, this is what is HFE into IB, and this is HIE, this is VBE and IB, and now VCE and IC. Okay, this is what is your simplified model. Okay, take it. I'll give you some couple of minutes to write all these things, but the point is, whatever we had seen till now, people call it as exact model. Now if you neglect few parameters, few H parameters, provided if RL is less than or equal to in the order of 4K, then go for simplified model, neglect HOE, and then neglect HRE. Basically, mathematically it doesn't have any meaning, but qualitatively it has some meaning, which is nothing but base width modulation. That part I will try to explain later, but let us take, because we started our H parameter model from two-port network analysis, which was basically a mathematical analysis. Therefore, this is also mathematically, but I explained a little bit with network analysis. If the load RL is in parallel to this, is almost, you can neglect this 1 by HOE. If RL is smaller value, it doesn't have any impact. Therefore, we are neglecting that. If you neglect that, we have to neglect HRE, where HRE is equal to 0. Okay, take it. Therefore, in the problem statement, remember, nothing will be given that you have to use simplified model. Based on the load value, you can go for simplified model. If load is in the order of 4K or less than or equal to 4K, yes, you can go for simplified model. Then indirectly, the HRE value, HOE value will not be given in the examination. What does it mean? We don't need for simplified model. Indirectly saying that use simplified model. You got it? Okay. That's what, when you solve multiple problems later on, using simplified model, you will understand. Okay. See, while writing your notebook, if you try to, whatever I just speak vocally, right, I cannot dictate all the points. Whatever you understood, right, while listening to the concepts of the circuits, what I'm drawing on the board, and you try to write running notes, okay? And I'm giving you sufficient time to write on your notebook, but whatever you understood, which I did not write, let us say, then you can write your own running note. That is very useful when you refer your notebook back, okay? Both are same only, but another representation. Just wire you can put here and there, but ultimately HIE should be there in between base to emitter, okay? This is base and this is emitter, and this is base and this is emitter, okay? I'll give you 3 more minutes. Maybe the continuation is, using simplified model, we should know the AC parameters of your common emitter amplifier, okay? I think I can stop for this session. In the next session, I think using simplified model, we need to see the all AC parameters related to common emitter amplifier. I'm going to give you only for common emitter amplifier from now onwards, okay? I'm not going to speak about CC amplifier. I'm not going to speak about common base amplifier. You know the reason, I told multiple times, okay? And in the examination, see, all these things, few of the concepts which we see are the few of the ways which we follow. A few things, they are driven by the problems what we are getting in the examination. Because to cover the problems, in what way if you speak or in what way we teach, therefore those will be solved. Therefore those things will drive us to explain in the format, okay? Because if you say that why we are not seeing simplified model for common collector and why are we not seeing simplified model for common base, not required, because with respect to practical analysis we don't need, we need only for common emitter configuration only. because that is what is my power gain or power boost circuit, which is what is providing huge power gain, which is what is taking more power from power supply, power gain basically. Okay, then let me stop here. Maybe 2 more minutes. The video will be continued, but it will be projected. You can if you want, you can draw it, but let me continue from next session. Okay.